Welcome to my video presentation. Have a good day to my lecturer, Puan Wan Amalia Wan Sulaiman, and all my friends. So today, I'm going to show you all a project which is about using derivatives of multivariable functions to solve a real-life problem. So now, let's check it out what the problem is. A farmer wants to maximize the yield of a crop based on the amount of fertilizer and water used. The yield with the symbol of Y in a unit tones is a function of the amount of the fertilizer, which have the symbol of F in unit kilograms, and the water with the symbol of W in the unit of liters applied per hectare. Now, we got a situation here. We have to maximize the yield of a crop based on the amount of fertilizer and water used. Thus, the yield function is given by Y in the bracket of F and W equals to 50F plus 100W minus 0.5 power of 2 minus W power of 2 minus 0.1 FW. As a result, we will model the yield as a function of these inputs, use partial derivatives to find the optimal amounts, and visualize everything with graph to understand how changes in fertilizer and water affect the yield. So, let's get started. First, we need to understand what is the function about. Imagine if a farmer managing a hectare of crops. The yield measured in tons depends on two variables, the amount of fertilizer in kilograms and water in liters. Due to this situation, we know that this is a multivariable function. Thus, each term has a meaning, like 50F and 100W. It shows how the fertilizer and the water boost the yield linearly. On the other hand, the square terms such as negative 0.5 F power of 2 and negative W power of 2 represent diminishing returns, like we got too much fertilizer or water that reduces the efficiency of the yield product. And then we got the negative 0.1 FW as interaction term, where indicating that the effect of fertilizer depends on the amount of water and vice versa. So, our goal is to maximize the yield, a multivariable function, by finding the optimal of F and W. So now, let's visualize the yield function. Alright, actually, I recommended to use the online software which is Desmos to draw this multivariable function. Desmos is a free online graphing calculator and math-based tool that is used in education settings to help students understand geometry and graphing concepts. It offers interactive features, visualization tools, and personalization options, making it a valuable resource for learning and teaching math. As it is a multivariable function and need to find its optimal point, thus we used to choose the 3D graphing calculator. As you can see on the right side, there's a blank graph. So what we're going to do is fill in the function in the left side column. Maybe you were worried about how to key in the math symbol. Just look at the bottom part. There's a keyboard, and then you can find what you want. Now, we key in our yield function onto it. Due to this 3D graph, we need to change the symbol of our variables. For instance, the fertilizer with symbol of F will change to X, while the water with symbol of W will change to Y. And then the yield in tons will be on the Z-axis. Since the yield with the symbol of Y doesn't affect, so will remain the same. As a result, the 3D graph of yield function is shown. It looks like a cylinder, maybe, but actually we can change this 3D into 2D with only one click of this icon. Due to this perspective angle, we can assume that the optimal point might be in the middle of this oval shape. Not only that, we know that the x-axis represents fertilizer, while the y-axis represents the water. Thus, the unit of these variables must be positive, so the answer will only happen in the first quadrant. But it is just only a prediction, okay? Now, notice to the highest point, which will be calculated later. Therefore, the shape suggests there's an optimal balance. At its risk, there are too little or too much of either input will lower the yield. Thus, this graph set the stage of our optimization. Now, we are going to start our calculation. To maximize the yield, first we need to find the partial derivatives with respect to fertilizer based on the yield function the question given. And now we can do dy df, and then is equal to 50 minus 5 minus 0.1 W, and also find out the partial derivative with respect to water. dy dw is equal to 100 minus 2W minus 0.1 F. Then find the critical points by setting the partial derivative equal to 0. After that, solve it by using simultaneous equation. First, we find out the equation of f and then substitute the f into the second equation. Complete the basic operation, open the bracket with the addition and minus, and then changing the sign from the positive to the negative, then do the division until we get the W. So the W is equal to 47.74 liter per hectare. So when we get the answer of W, we can substitute into the first equation. And finally, we get the answer of F is equal to 45.23 kg per hectare. So far, we already have the answer of F and W. And now, compute the yield. Substitute the F and W into the yield function. After all the calculation, we will get Y is equal to 3,517.8 tons per hectare. Until here, actually it's done. But we need to confirm that whether the answer we get is at the maximum value by using the Hessian matrix. Thus, we need to find out the second derivatives respect to F. Just refer back the partial derivatives and do the derivation again. So this is the partial derivative respect with f, and then do it again respect to f, and we will get -1. Do it the same with the partial derivative respect with w, and do it again respect with w, and we will get -2. After that, find out mixed partial derivatives respect to other variables. For the first one, the partial derivative with respect to f, then respect to w, we will get -0.1. On the other hand, the partial derivative with respect to w, then respect to f, we will get -0.1. Without an exact second, two of the answers were absolutely the same. And now finally, we can find the Hessian matrix. Although the formulas seem complicated, but actually we have already fulfilled as the terms it needs. Then just substitute onto it. Calculate the determinant of the matrix with cross multiple and sum it up. After the calculation, we will get the answer is 1.99. So the determinant of the matrix is positive as it's larger than 0, while the second derivative is smaller than 0. It's proof that it is indicating a peak. Therefore, the critical point for f and w is equal to 45.23 and 47.74, and they are known as local maximum. Alright, so far the calculation is done. Let's explore the partial derivatives visually. Here's the equation dy df is equal to 50 minus 5 minus 0.1 W. This shows how yield changes per kilogram of fertilizer added. When f is small, the derivatives is positive. It means that the increasing of fertilizer can boost the yield. When f equal to 45.23 with w equal to 47.74, it becomes 0, which is already marking the peak yield. Beyond this, it will become negative, as there are no fertilizer reduces yield due to the overuse. Now, for the equation dy dw equal to 100 minus 2w minus 0.1f. Similarly, the yield is positive for small w until it becomes 0 when w is equal to 47.74. Rather, it's become negative for larger w, which means that it is indicating too much water and harms the crops. As a result, this plot confirms our critical point is where both rates of change balance at 0. So it is maximizing the yield. At this stage, there might be some justification here. Why do the partial derivatives behave this way? Think about farming. With little fertilizer, adding more boosts crop growth. Thus, dy df represents the rate of change of yield respect to the amount of fertilizer used. So, dy df is positive, but too much fertilizer does overwhelm the soil and burn the plants. It will reduce the yield. Hence, as the fertilizer increases, dy df decreases, is indicating diminishing returns for fertilizer. Furthermore, the terms -0.1 W in the yield function shows water influence, which means that the more water used, the lower the fertilizer's marginal benefit slightly. So for the water, the story is similar too. With small amounts of water help plants thrive, but excessive water will cause water lodging or nutrient runoff. Thus, dy dw represents the rate of change of yield respect to the amount of water used. As water increases, dy dw decreases. is indicating diminishing returns for water. In addition, the mixed partial derivative is equal to negative 0.1 indicates the increasing of one input will slightly reduce the marginal yield of the other input. However, when M is equal to 45.23 and W is equal to 47.74, the derivatives are zero. It is perfectly balancing both inputs for maximum yield. Thus, this graph visualizes clearly for those trade-offs. As a result, this mirrors how farmers adjust the input to avoid waste and maximize the harvest. In the conclusion, we maximize crop yield at approximately 45.23 kilograms of fertilizer and 47.74 liters of water per hectare, achieving about 3,517.8 tons of crop yield. As a result, using partial derivatives, we found the sweet spot balancing fertilizer and water, and our graphs show us how the yield responds to the changes. Last but not least, we are able to demonstrate how calculus can be used to analyze and optimize changes in crop yield based on input levels by showcasing the power of calculus in understanding and managing change in real-world system. In the end, I hope you all like this video, and I also hope you are inspired to apply this tool to other optimization problems. Thanks for watching. Bye bye.